Okay, I think it's time to start. It's my pleasure to have Rosa here. She is a new postdoc at the IFT, and she has recently obtained her PhD in Argentina at the Universidad Nacional de San Martín on BSM phenomenology at LHC, and today she's going to talk about C-prime model phenomenology and confronting with LHC data. Thank you very much, Rosa.
Thanks to you. Oh, hello, everyone. It's a pleasure for me to be here today in the place that is going to be my house for the next 2.5 years. As Ernesto has said, I'm going to present Z-Prime Explorer, a software for confronting Z-prime models against LHC data. Following the spirit of the seminar, first I'm going to give you a brief introduction about the standard model and the motivations for the search of new physics. Also, we talk about direct detection experiments and the available reinterpretation codes that is the task to confront all the theoretical models that we have against the experimental data. Of course, I will talk a little bit about the Z-prime boson, and then I'm going to present our software. I will explain how does it work. This first version is for confronting Z-prime models against visible LHC data, and with visible we refer to two possible standard model final states. And also I will introduce Z-Prime Explorer 2.0, which is the latest update, which includes a minimal extension to dark matter sectors, including the possibility to have a Z-prime boson as an S-channel mediator to fermionic dark matter. So let me start from the beginning. In particle physics, the standard model, it's the most complete theory that we have up to date to explain the fundamentals or the fundamental structure of matter, and also to explain all the fundamental forces that we know based on the ideas of symmetry and gauge invariances. In this, the standard model proposed a Dirac-Lagrangian where quarks and lepton are the fundamental objects of the matter, and to introduce the fundamental forces, three local gauge symmetries are needed. And when rewriting the covariant derivative of the free particle Lagrangian as a consequence of the imposed invariances, the interaction, the fundamental forces are understood as an interaction between the matters of fields and through the interchange of the so-called gauge bosons. And to be able to give mass to all the massive elementary particles, we have to add an extra scalar boson to the theory, the Higgs boson, to be able to give mass to all the elementary particles through the so-called Higgs mechanism. But even its formal development in the 70s, all the experimental data firmly agree with the standard model predictions. There is still a lot of phenomena that's not explained by the standard model. For example, the gravity is the only known fundamental force that it's not included in the theory. There are no hints about dark energy and dark matter, which are a hypothesis that came from cosmological observations. Nothing is explained about neutrinos oscillation, which implies that neutrinos have masses, and there's no hint neither about the baryon asymmetry in the universe. We know that we have more matter than antimatter in the universe. To all these unexplained phenomena, we also have some theoretical questions that goes beyond the number of symmetry of why the theory has the number of symmetries that it has. We also have the problem of the hierarchies in the calculation of the Higgs mass, the strong CP problem. So all these issues point toward the need to search for new physics, not only to see if there are new particles, new phenomena that we haven't observed yet, but also to test all the beyond standard model proposals that appear for trying to explain one or more of these issues. The search of new physics at hadron colliders, such as the LHC, constitutes an extensive program. I dare to say that maybe it's one of the most important programs at the LHC. We are in an era of unprecedented precision thanks to the energy and the luminosities that we have reached. And let me now talk about direct detection experiments, where we look for hypothetical possible new particles. In this kind of detection experiments, we try to estimate the on-shell resonant mass of the new particle through the reconstruction of this particle from its decay products. So the challenge in this kind of detection experiments is put on the reduction of the possible backgrounds that can be confused with signal. Of course, we use all the event selection, the proper event selection criteria to achieve this. And from these searches, we have both model dependent and model independent limits that are complementary to constrain all the VSM proposals. Model building require compare the parameter space of a given new physics model against a large and ever-growing variety of experimental constraints. And this task can be really difficult. But it's highly non-trivial because it depends on several factors. We have the assumptions of experimental searches, the model independence of the limits. We also have the public availability of the necessary information to reproduce the limits outside the collaboration. So to ease this task, there are many reinterpretation codes that helps the theorists, the people that work in theory, to compare their new physics models against LHC data. Basically, we have like two broad categories. First, we have general codes. In these general codes, any LHC study can be implemented, and the results apply to arbitrary models. So this flexibility has the price of having to generate a large number of Monte Carlo events to confront only one benchmark point within the parameter space of the new physics Lagrangian. We have, for example, in this category, checkmate, math analysis 5, and gambit, for example. And on the other hand, we have dedicated codes which focus on a specific model, framework. And this narrows the applicability and allows to bypass the CPU time consuming the event generation, and allows a faster exploration of the parameter space of the given new physics model. Examples are Higgs bounds, Higgs signals, S model S, and Z prime explorer belongs to this later category. So our software is based on these hypothetical new particles, the Z prime boson. It has this name because it has the same quantum numbers that the standard model Z boson. Is a massive spin 1 particle, electrically neutral and color singlet. Possibly it's one of the favorite candidates in the new physics model because it can be simply added to the standard model Lagrangian just by adding an extra U1 prime symmetry to the ones that we already had in the standard model. Of course, there are more complex ways to incorporate this boson to the standard model Lagrangian. We can see this kind of more sophisticated procedures in string theories where composite models, Kaluza-Klein, Little Higgs. But in any case, we can always write the interaction term between the Z prime and all the standard model fermions like this, effectively like this, using two effective couplings, chiral couplings to each of the standard model quarks. To each of the standard model fermions. And of course, we also have as free parameter the Z prime mass. And this effective Lagrangian is what allows us to build our software. So keep this Lagrangian in mind for the next slides. Set prime resonance is produced at hadron colliders such as the LHC through quark-antiquark annihilation. So its production cross-section will depend on its coupling to valence and C quarks in the proton. Set prime resonance cannot be produced at loop level through gluon fusion because of the Landau-Yang theorem, because it's an spin-1 particle. Set prime decay modes and branching ratio also will depend on the specific mu physics model, but in principle we can have possible decays to all standard model fermions, to charged bosons, to neutral bosons, and eventually any other non-standard model new particle. Of course, once again, this kind of decays are forbidden for the same reason that we have in here. At the LHC, set prime searches have been performed both by the CMS and Atlas collaboration and have superseded the results coming from other colliders such as Tevatron in most of the TeV scale. And at the current situation at the LHC, all the possible visible channels have been explored. And although the fraction of time given set prime decays on a specific channel will depend on the corresponding branching ratio, that of course will depend on the parameter structure of the given mu physics Lagrangian. In experimental terms, the acceptance and the efficiencies of the detector as well as the background of the given channel are crucial to determine its exclusion or detection sensitivity. And all these features also depend on the energy scale of the resonance, because we know that the techniques for detecting and reconstructing particles also depend on the transfer momentum regime of the final state particles. So determining what is the most sensitive channel, what is the best channel to look for a given set prime within a given set prime model can be highly non-trivial, and this is the main motivation behind the creation of our software, which allows to make a quick comparison between the sensitivity of all visible channels for a given set prime mass. That's how was born Set Prime Explorer, the software that we create together with my PhD supervisor, Ezequiel Álvarez and Mariel Esteve. It's publicly available on GitHub, it's open source, and of course it's free. The code runs on C++, and the code runs on C++, and it's really simple to use because the user only has to provide an incard, which is a text file, specifying for each benchmark point that he or she wants to explore the set prime mass, the effective coupling to all standard model fermion, both quarks and leptons, and the partial width to neutrinos, charged bosons, and neutral bosons. We require this later information as partial width, since there is not a unique Lorentz structure in their couplings, as we have in the other case for the fermions. And also the total width to non-standard model particles can be added in the computation, since this total width can change the branching ratios of the visible channels. To execute the program, the user only has to write this instruction in command line, and after execution, the output, which is also a text file, contains the strength of the signal of each visible channel for each benchmark point at the LHC and at 13 TeV. Additionally, we give the total width of the set prime under consideration, and a warning in the case that the ratio the width to mass ratio is higher than 5%, because our framework, our results are valid only under the narrow width approximation. But let me explain you now what is this strength, what is this phenomenological magnitude that allows to compare the sensitivity of all channels. It was of particular interest for us to find a magnitude that condenses all the relevant theoretical information of the given new physics model and the experimental cleanliness of the signal of each channel. So phenomenologically, we can define the strength of a given channel as the ratio between the prediction for the cross-section times branching ratio for a given channel and the corresponding 95% confidence level upper limit for this magnitude that can be extracted from the latest ATLAS and CMS results. And despite the complex compromise code in its definition, the interpretation of this strength is really simple, because if the strength is higher than 1 in a given channel, the benchmark point is experimentally excluded by the channel or the channels where the strength is higher than 1. But if the strength is lower than 1 in all channels, the benchmark point is not only not excluded, but also the channel with the largest S is going to be the most sensitive for the Z prime detection or exclusion. And another interesting feature about our software is that it's really fast, because for 10,000 benchmark points, there are no more than 5-second performance is required in an ordinary laptop. But let me now describe a little bit the backend of the software to understand why our software is that fast. Well, the first task performed by our software after execution is the estimation of the production cross-section for the benchmark point under consideration. Basically, the software used previously generated and recorded production cross-section with MATLAB, with a tailored model which couples with unity to only 1 quark in the proton each time, and for a set of Z prime masses between 0.5 and 8 TeV. This is basically the range of Z prime masses that can be explored within our framework. And these calculations are stored in our repository and are used during program execution. The total cross-section, the total production cross-section, is going to be the sum of the 5 contributions in the quark, each of them adjusted by the sum of the corresponding square chiral couplings that are extracted from the in curve. And then with this production cross-section, under the narrow width approximation, we can estimate the total prediction for the given channel just by multiplying by the corresponding branching ratio. The experimental limits are extracted from the latest ATLAS and CMS results at 13 TeV. In each case, we take the most sensitive search. Sometimes for some channels, it's the ATLAS one, and in other cases, it's the CMS one. We store the 95% confidence level expected upper limits of the production cross-section times branching ratio in terms of the Z prime mass. Of course, we store this information as one-dimensional grids where the Z prime mass is the free parameter, and we use the expected limits instead of the observed ones, because we want to consider experimental techniques instead of eventual fluctuations in data. Of course, this is an approximation that is valid as long as no large fluctuations are present in data, which is the case in all the visible channels that we are including that we have included in the first release of our software. Let me now show you some applications examples. First, we test our software using the sequential standard model, which is a typical reference model in experimental searches for its simplicity. In this model, the Z prime couplings to all standard model fermion with the same couplings than those of the Z prime of the standard model Z boson, and it was for us a very interesting example to validate our software. We see in this plot the strength of each channel, of each visible channel in terms of the Z prime mass. Of course, if the strength is higher than 1, in a given channel, the Z prime mass is automatically excluded. So if we see the area where the strength is lower than 1 in all channels, we see that only masses above 5 TeV are allowed, which is actually the public limit that you can find the particle data group and in the experimental searches. So we consider it as a second validation of our procedure. But the output is further more interesting when we have more than one free parameter. So we decided to test our software using a B-L model where the U1 prime symmetry is associated to the barium minus lepton model. In this case, we use a version of this model that was first introduced in the literature in 2015. In this case, we have two free parameters, the coupling associated to the new gauge symmetry and the set prime mass. And in each point, we try to indicate what is the most sensitive channel according to the shape of the point. In this case, for example, in this point, the most sensitive channel is the die-shaped channel. And if the points are in black, they are experimentally excluded because the strength is higher than 1 in this point of the parameter space. And you can see how interesting is the interplay between the electronic channels and the hadronic channel. And you can see that the output is furthermore richer than for this other case that we only have one free parameter. But let me now introduce the update of our software, Set Prime Explorer, a work that we have done in collaboration with Victor Martin Lozano and Jose Zurita. The main novelty in this second version is the inclusion of a minimal dark matter extension, where we allow the possibility to have a set prime boson as an S-channel mediator to fermionic dark matter. And this kind of decays are invisible, of course, so they are related to mono X searches in experimental data, because we need like an extra standard model particle for the event to be triggered, because the decay is invisible. And in this kind of minimal extension, the X particle comes exclusively from initial state radiation, and it has been shown that in this case, the monoshed search trumps over all the other searches. So we just focus on the missing energy plus searches. We made the first public reinterpretation of the latest Atlas monoshed search at 13 TeV and 139 inverse femtobars. In this search, we have bounds for an axial vector or vector dark matter mediator in the two-dimensional plane given by the masses of the dark matter particle and the set prime mediator. And they give the exclusion contour lines with a fixed coupling structure. They also are considering a universal coupling to all standard model non-fermions. So in principle, extracting the limits from this kind of plots, it's highly non-trivial, because we now have a two-dimensional plane. We do not have directly the information about the limits in the cross-sections. And also we would like to extend these results for an arbitrary coupling structure. So let me talk a little bit about the reinterpretation that we made for this search to understand a little bit why we changed some things for this update. In this search, the analysis is performed in exclusive regions with increasing transfer missing energy. They divide the events depending on the transfer missing energy of them. So our first task was trying to reobtain the missing energy, the missing transfer energy distributions for the benchmark point report by Atlas. They only report this distribution for this point where the dark matter mass can be neglected. And we see that we perform our simulations using MATLAB, PIDIA, and Delphis for detector simulation, using the Fein rules that corresponds to the dark matter simplified model used by Atlas. And we see that we need a global K factor of 0.8 to match the Atlas distribution after applying event selection criteria. But we know from the recommendations of the reinterpretation forum that to validate this kind of K factors, we need at least one additional benchmark point. But unfortunately, Atlas does not give this information. So we need to go to a previous work at lower luminosity. We extract another benchmark point from this search. And they use, of course, the same model. And in this case, once again, considering the error, we obtain the same K factor. So we consider our event generation pipeline as validated. Then with this global key factor in mind, we try to reobtain the exclusion contour lines for the exclusive regions with increasing transfer mean energy. We could match the 95% confidence level upper limit report by Atlas using the formula for the significance in the Gaussian limit, because we are in the regime where the signal is much lower than background and the background is much higher than 1 in all exclusive regions. Of course, in each point, we divide the events in exclusive region, and the one with the highest significance is going to be the most sensitive. And now let me explain how we incorporate these results to our software. Basically, the front end doesn't change too much. We only add now as an extra requirement the mass of the Dirac dark matter, of the fermionic dark matter particle, and it's coupling to the Z prime boson. And the output, of course, now we are going to have also the strength to the monoshed channel that is associated to this minimal extension to the dark sector. And the backend just changed a little bit. Now, in the production cross-section, we have to estimate also the production of the shed that is going to be the initial star radiation for our process. So in here, now we have to consider the whole process, proton-proton to Z prime shed instead of just QQ bar as we had for the visible channels. And this is because now we have gluons involved in the production cross-sections. And then once again, under the assumption of having an arrow with Z prime, once again we have the prediction for the cross-section of the monoshed of this dark matter channel. This cross-section is used to rescale the expected limits that we extracted from the reinterpretation work that we have performed from the latest Atlas search at 13 TeV. We store the signal events for each exclusive region in a two-dimensional grid, where the two free parameters are the Z prime mass and the dark matter mass, And we store these signal events for the benchmark point used by Atlas, and we properly rescale those signal events using the prediction for the new cross-section and the prediction for the cross-section for the benchmark point used by Atlas. And then with the signal events properly rescaled, we estimate the new significance to get the strength of the monoshed channel. So this is the results, the kind of plots that we can obtain using the dark matter simplified model used by Atlas. In here, this is the benchmark point used by them, and we can see the interplay between the monoshed channel and all the standard model visible final states. And it's interesting because now we can change this universal coupling, and we can see how change the behavior, and now there are more areas that are allowed by the current experimental searches. But for us, it was more interesting to go to a more generalized scenario. And now we try to play, assuming that we have a new non-universal coupling to all standard model quarks. We try with tophilic Z prime mediator. Of course, we need an extra coupling to up-type quarks because we need the Z prime to be produced. And in this case, when the Z prime couples predominantly to top quarks, we can see that not only the die-shed channel loses some sensitivity, but also the monoshed channel could be the most sensitive in a large area of the parameter space. And we also drop the assumption to have a leptophobic mediator, and we see the possibility to have a leptophilic Z prime mediator. And of course, we clearly see how sensitive are the lepton channels, and we can see that if they are open, they can dominate the exclusions. So there's a lot of information condensed in this kind of plots. I don't want to take much time. I don't want to bother you. So let me just go to the conclusions. The first version of our software, Set-Prime Explorer, determines the most sensitive channel, visible channel, for the exclusion or the detection of a set prime at the LHC within the narrow width approximation. It is smart because it only uses this phenomenological magnitude, the strength, and all the available experimental bounds. It is fast because no Monte Carlo simulation is performed, and all the calculations are analytical, and simple because only requires from the user an in-car with couplings, masses, partial width. And the update of our software includes a minimal extension to dark matter sectors, allowing to have the possibility of a set prime mediator as to fermionic dark matter. And thanks to that, we could make the first public reinterpretation of the latest Atlas monoshed search and extend it to arbitrary coupling structures. So our idea is to include other mono X searches in the future. Of course, this will allow us to include more general dark matter scenarios with more than one dark matter particle. In this case, final state radiation also plays an important role and must be taken into account because the monoshed signature is not going to be the predominant no longer. Also, we have the idea to include possible next to linear order effects, searches for working with flavor changing neutral currents. I mean, there are a lot of possibilities. We are willing to have new collaborators. So thank you very much for your attentions, and I'm all yours for your questions.
Okay, I think we have time for comments, questions.
Yes.
Could you please go back to the plots?
Yeah.
Because I was not able to understand the color code. Sorry.
Oh, okay, yes. The most sensitive channel in each point is going to be determined by the shape of the point. And if the point is in color, then the point it's still allowed by the most sensitive channel is going to be the one that corresponds to its shape. And if the point is in black, the benchmark point is experimentally excluded. So we can see all this condensed information in this kind of plots. Another question?
Actually, I have something else.
Yeah.
Because when you were saying about the production,
Yeah.
you are considering only Reobtaining production.
Yes.
So have you thought about consider something like vector boson fusion or things like that?
No, because for the Landauerian theorem, this kind of production is not available. Since the set prime boson is a spin one particle, we can have this kind of productions processes.
But what I mean, it will be like this second decay diagram that you are having.
In here. Oh no.
The one in between. So
This
basically,
one.
you are having for each proton, you have W.
We check the probabilities, the contribution to the total production cross-section. It's can be neglected in these cases.
What I was having in mind is that, for instance, for Higgs invisible decays, the vector boson fusion is the dominant channel for these searches. So maybe if you include that, you could recast.
It could be a good extension, maybe, yes. No, we haven't checked on that, I must confess. But it could be interesting. I have no doubt. Any other questions?
Yeah. Are you planning to update the code with every analysis from Atlas and CNS and update?
That's the idea. Yes. In fact, in the second version of our software, we update all the searches for the visible channels. Yes, that's the idea. Keep on updating
Okay. And I have another question, a curiosity. When you saw the plot with the net missing transfer energy.
Yes. Just 1 second.
Yeah.
Here.
With why the last beam is larger than the previous one?
Why the last beam? Sorry.
The last beam with the largest energy?
Yeah.
No.
Here.
Yeah, on the left.
Because it's the last bin, it's inclusive. They include all the events with.
Okay.
Yeah, that's the difference.
This square. Yeah. I understand.
It's nothing else.
It's not a fluctuation.
No. Okay. And in this case, in the previous search, we do not have this exclusive region. The division is different. That's why the reason that why we see different ranges. Yes.
I have a question, actually. Coming back to the Landau-Young argument you made.
Yeah.
I remember there was a discussion whether the Landau-Young theorem applies when you have theorems.
Yes. We include this discussion also in our publication, but we decided to ignore this possibility because it doesn't change much the results that the kind of results that we wanted to. But we discussed this idea also in our publication.
But if it is allowed to happen, why does not happen? Why does it not happen then? Because immediately we have a lot of gluon fusion production.
Yeah, but we are considering a color singlet set prime. So I know that I don't remember much about the discussion, but I guess that it's an interplay between the colors of the gluons and the set resonance. And I remember that we just ignored this possibility because of that. It was, sorry, I'm not an expert in the QCD area, so I cannot give you further information.
So what happened with gluons?
I noticed that the proof of the Landau-Young theorem assumes that the photons have gluons instead of photons. For instance, you can have a color object that can have a massive vector with object. The discussion was whether the proof extends to color singlets or not. This was unclear as far as
we are just considering.
I don't remember the details, but I do remember that we could have a color set prime for sure.
Yeah, but we are not considering. We are just considering color singlet.
For the singlet, I remember it was.
Yeah. That's exactly. Thank you. Any other questions?
Question, comments?
Yes.
A bit of a technical question, but you said the code is written in C++.
Yes.
Since everything is analytical and the code is anyway fast, why not use Python, which is a bit easier to maintain?
It was just a bad decision at the beginning, and then we have to continue with this bad decision. But yes, originally we had this discussion also. Yes, I also prefer Python.
It's a bit easier to maintain.
You know, once that you understand the code, it's the same. But at the end of the day. But it was a discussion that we had.
More question? Okay. Pretty nice seminar.
Thank
Rosa.
you so much.
Gracias, Karen.
Yeah.